Hello, welcome to Lecture 17, Part 1a. I divided Part 1 of Lecture 17 into two parts because the last part of this lecture has a little bit of mathematics in it. We want to talk a little bit about osmolarity, about equivalence, so I wanted to spend a little bit of time with that and not overwhelm you with a very long video. Lecture 17, Part 1 has actually Parts A and B. What we want to talk about in this part is we want to just get an overview of what we're going to be talking about in Lecture 17 with regard to fluid, electrolytes, acid-base balance. We're also going to talk a little bit about body compartments, exactly what they are and what they mean. And then we'll go on and talk a little bit about osmolarity and about equivalence. These are important kind of foundational concepts that you'll need to have regardless of what program you eventually wind up going into. This material is going to be from Chapter 26 in Marib. Incidentally, I wanted to show you this just in case you need a little bit more help with osmolarity. This is our web page on the gsariani.com website. And if you scroll down to the lectures on water, electrolyte, acid-base balance, and really just before that with the urinary system, you'll see that there's an osmolarity, tonicity, and equivalence study guide that I generated for you. And there's also a link to one that's on the Wisconsin online site. I thought was pretty good. So if you need some additional help with that, you can take a look at that, okay? Okay, so let's begin with an overview of what we're going to be talking about. First of all, we need to know that our survival really depends upon maintaining a normal volume and composition of both the extracellular fluid and the intracellular fluid. Now, extracellular fluid, as you can imagine, is all the fluid that's outside of cells. Intracellular fluid is all the fluid that's locked up inside the tiny cells in our body, all 70 trillion of them. And ionic concentrations of body fluids are extremely important, as is pH. And we'll come to this when we talk about acid-base balance a little bit later in Lecture 17. When we talk about these concepts, you notice that the title of the lecture was Water, Electrolyte, Acid-Base Balance. And what we're really talking about are three interrelated processes. The first one is fluid balance, and what we're really asking here is how does water move from one place in the body to the other? We also want to talk about electrolyte balance. What's an electrolyte? If you remember, those are inorganic charged particles that make salts in the body, and we call those electrolytes. These can conduct electrical current, as we said. And then finally, we have acid-base balance. And here we're talking about really predominantly hydrogen ion and bicarbonate ion, as we'll see, and the balance between those two. Recall that normal pH of body fluids and blood plasma is 7.4 on average. The range is 7.35 to 7.45. So you'll notice that each of these terms that we're talking about has the word balance in it. And if you remember from the lectures on nutrition and metabolism, we referred to the term balance as being the amount in equals the amount out. So we're really talking about something very, very similar here with regards to fluid, electrolyte, and acid-base, as we'll talk about a little bit later. Now, the other thing I want you to notice is that we say that these are interrelated processes. It's important to realize that although we talk about these processes as if they're separate things, the reason we do that is really just to learn about them. But when you start dealing with clinical processes that are going on in somebody's body, and one thing goes wrong, it will affect the other things. And so in other words, these processes are all related in the body. The only reason we separate them out and talk about them individually is so that we can get a clearer picture of them and learn a little bit more about them. Okay, let's talk first about water content of the human body. As you see, we have about 40 liters of water in an average body. And this percentage of water composition in the body varies according to the gender, according to age. As an example, infants may be up to 70% body water, primarily because of their decreased bone mass, the decreased amount of fat, which you'll remember doesn't hold any water. In adults, when we talk about adult males, we may be talking about 60% body water. In adult females, maybe 50% body water. And one of the reasons why females have a lower percentage of body water is because, in general, they have a higher amount of body fat, and they also have a little bit less muscular mass. When we talk about elderly people, they can have body water as low as 45%. And one of the reasons for this is the large decrease in muscle mass that typically accompanies aging. Now you notice of the 40 liters of body water that we have, 1/3 of it is extracellular. So 1/3 of 40 is 15. 2/3 of this body water is intracellular. That is locked up inside the cells of the body. Now, this might seem a little odd to you to have most of the water inside body cells. You know, when you say to yourself, the body cells are so tiny, how can most of the body water be inside the cells? Well, what you have to remember is that there are so many of them. We're talking about someplace between 70 and 100 trillion cells. And although each one of them has only maybe a femtoliter inside it, this is when we add that up and multiply that by 70 trillion or 100 trillion, that works out to about 25 liters of water locked up inside the cells. Now let's talk a little bit about fluid compartments and where all this water actually is. One of the things you'll notice on this slide, this is a nice diagram. I like this one. This is not from our book. It's from Hole's Human A&P. But you'll notice once again that of all the composition of body water, we have about 2/3 inside cells. And on the right lower portion here, you can see that we have 1/3 is outside cells. Remember that the water that is outside cells we refer to as extracellular, and that's inside cells we call intracellular. Now, one of the distinctions I want to make here is all along since A&P1, we've been using the terms extracellular and interstitial as being the same thing. They really are distinct. If you notice, interstitial fluid, which you see up here, is actually the fluid that surrounds and bathes the cells of the body. When we talk about extracellular fluid, notice that that includes the interstitial fluid, but also includes things like plasma, like lymph, and what we call transcellular fluid, which is fluid that moves between the different compartments in the body. So there really is a distinction between interstitial fluid and extracellular fluid. Extracellular fluid being the encompassing one that includes interstitial fluid. Now this next point is important for you to kind of comprehend. The compartments that we see above commonly behave as distinct entities in terms of their ion distributions. However, the intracellular fluid, ICF, and the extracellular fluid, ECF, the osmotic concentrations they maintain are identical. And remember, we talked about osmotic concentrations when we talked about the urinary system. Let's use, just because it's a nice round number, 300 milliosmoles per liter. Now the question is, although these individual compartments have different concentrations of ions, why is the osmotic concentration identical between all the compartments and maintained at about 300 milliosmoles per liter? Well, the reason for that, if you think about it, is in most places in the body, except those we looked at in the kidney when we studied those, water is free to move between compartments. So water is completely free to go from here to here and move in between, from here to here, as we'll see in a moment, from here to here, so on and so forth. So whenever we have the movement of a salt or a solute from one compartment to the other, water is going to follow along. And typically in most parts of the body, water is free to move between compartments. This is the reason why the osmotic concentrations between compartments are identical, in spite of the fact that we maintain different ion distributions across the compartments. And just to give you an example of that, if you remember when we talked about neuroscience, we talked about the fact that we have a high concentration of potassium inside cells and a low concentration of sodium. It's reversed outside. Here we have a higher concentration of sodium ions and a lower concentration of potassium. Just to give you one example, there are many, many examples of ion concentrations that differ between and among the compartments, but this is the best example because this is something we've already talked about. So we maintain different ion distributions, however the osmolarity is equivalent or equal between the compartments. Now the next thing we want to talk about is an important concept called osmolarity. We're going to come back and talk a little bit more about the definition of osmolarity. I know we defined it already, but we want to come back and talk about it just a little bit more, and I'll do that in the next slide. What I want to do here, though, is just talk a little bit about the osmolarity of the body. And if you remember, we said that the osmolarity of body fluids is roughly about 300 milliosmoles per liter, and this is about normal. This varies depending on what textbook you're reading, anywhere from maybe 265 up to maybe 305 milliosmoles per liter. I like to use 300 because it's a nice round number. As you'll see, we're going to do a couple of calculations with this. Now the volume of water, if you remember from what we just talked about a second or two ago, was 40 liters in an average adult. So we have 40 liters of body water, and this gives a concentration of 300 milliosmoles per liter. The question we have, though, is how much solute do we have in the body in order to get us this osmolarity? And basically all we have to do is, if this amount of solute is the unknown, we multiply both sides here by 40 liters. The 40 cancels out over here. And if we multiply this by 40 liters as well, you notice the liters cancel out. And 40 times 300 gives us 12,000 milliosmoles of solutes. So we have about 12 osmoles, or 12,000 milliosmoles of solute, distributed across 40 liters of water throughout the body, and that gives us an osmolarity of 300 milliosmoles per liter. Okay, that's a pretty simple calculation. Now let's take an example, and just to see how this works. One of the things we always like to do, as you know, is we like to establish relationships between things. So what would be the relationship between a change in the solute concentration and the osmolarity? Sure, as you can see, since the amount of solute is on the top of this fraction here, if we increase the amount of solute, we also increase the osmolarity. So we would say that these are directly proportional to each other, or directly related to each other. On the other hand, let's take a look at what happens if we increase the volume of water. This now is in the denominator of this fraction, and we know that since this is down here, if we increase this, we decrease this. So basically, a decreasing osmolarity is a decreasing concentration of solute. And that makes perfect sense when you think about increasing the amount of water in the body. We're decreasing the concentration of solutes, and so we say we're decreasing the osmolarity. On the other hand, increasing or decreasing the amount of solute will go hand in hand with the osmolarity. If we increase the amount of solute, we're increasing the concentration of body fluids and increasing osmolarity. If we decrease the amount of solute, we're decreasing the concentration and decreasing the osmolarity of body fluids. Hope that makes some sense to you. Now let's just do a couple of quick calculations to look at this. Let's say that we wanted to figure out what the osmolarity was going to be in the body. If, for example, somebody started out with a normal 12,000 milliosmoles of solute distributed across the 40 liters of water that we typically have in the body. Let's just say that somebody ate a bag of salty chips and didn't do anything about their water. In other words, all they did was eat the salty chips, but they didn't take in any water. And let's just assume, and this is roughly correct, let's just assume that a bag of chips has about 800 milliosmoles of salt in it. So what would be the new body osmolarity if no water was taken in with the chips? Well, if we do this calculation and we look at what 12,800 milliosmoles of solute is divided by 40 liters of body water, we come out with a new osmolarity of 320 milliosmoles per liter. So you can see that since we've increased the solute, we've also increased the osmolarity. So this is what we said above about how these two things are related. Now let's take a different example and let's figure out the osmolarity. This time though, what we're going to do is we're going to change the water. We're going to assume that we have the normal 12,000 milliosmoles of solute in the body. And now what we're going to do is start out with the 40 liters of body water and add 1 liter of body water to that. That's going to give us 12,000 milliosmoles divided by a total of 41 liters of water. And when we do that calculation, we come out with about, rounding it off, about 293 milliosmoles per liter. So once again, you can see the relationship between volume and osmolarity. So if we increase the volume of the water, we decrease the osmolarity. In other words, we dilute the concentration of salts in the body. So there's one other thing I want to talk about, and that is the fact that we use the term osmolarity, remember, because we have different kinds of solutes dissolved in body fluids. So that begs the question then, how do we kind of sum up the osmolarity? We found out that there's 12,000 milliosmoles of solute in the body constituted by all of these different kinds of solutes. So how do these osmolarities sum up? Well, it really is very, very simple. What we basically do is we sum up the osmolarities of the individual components in a solution. For example, if I had 1 osmole of sodium in a solution and I had 2 osmoles of, let's say, potassium in solution, and I had 3 osmoles of glucose in a solution, I would have a total of 6 osmoles of active particles in a solution. It's as simple as that. So once we get all the osmolarities, we get the number of osmoles that we have, we can basically just sum those up to get a total osmolarity of the solution. Hopefully that makes a little bit of sense to you. Now if you want to try something on your own, give this problem a try. Let's say a weekend snacker consumes a bag of salty chips, and let's say that contains a total of 900 milliosmoles of salt. So what we'd like to know is how much water must you drink in order to restore body fluids to the normal 300 milliosmoles per liter after you take in about 900 milliosmoles of salt. Give it a shot. It's not too hard. You might have to just think through it a little bit, maybe rearrange the equation a bit. But think through it and try to get the answer and see what you come up with. Now, the next thing we want to do is just redefine osmolarity. We've talked about this before. But there are a couple of additional things that I want to do here and talk about a couple of additional concepts. So let's first start with the fact that osmolarity expresses the total solute concentration of a solution. Now, as we said before, remember we can't use molarity like we do in chemistry, because when you use molarity, you're talking about one entity, one thing. However, in the body, remember, we have a bunch of different kinds of solutes that are dissolved in body fluids. And so we can't use molarity because it doesn't work quite well. So what we have to do instead is use osmolarity. So we basically take the combined molarities of all these different solutes in the body, and we have this term that's called osmolarity. This basically is going to have a dramatic effect, as we just saw before, on water, on the water content of body solutions. And this is determined, as we said earlier, from the number of dissolved particles, and this is an important point regardless of where they came from. Remember, we're not making a distinction between the types of particles. We're only considering the number of particles. And that's important for you to understand. Okay, let's look at a couple of other things. The term osmol reflects the number of particles yielded by a particular solute when it goes into solution. And as you can guess, when we talk about osmol, we're talking about the major unit, but we can also talk about milliosmoles, which are basically 1/1000th of an osmol. And we abbreviate that, as we've done in the previous couple of slides, as MOSM, like this, milliosmoles. Now, let's take a look at a couple of different things. I'm going to describe these first, and then I'll illustrate just to show you how this goes. If we put 1 mole of glucose in a solution of water, we know that the formula weight of glucose is 180 grams per mole. If I put this in a beaker of water, what I'll wind up with is 1 osmole of particles. In other words, if I put 1 mole of glucose in 1 liter of water, I'd wind up with a 1 osmolar solution. On the other hand, if I put 1 mole of sodium chloride in 1 liter of water, what I'm going to wind up with is a 2 osmolar solution of sodium chloride. I'm going to draw that out in a second. But the basic formula that we use in order to calculate osmolarity is the number of moles per liter multiplied by the number of particles that that particular thing yields in solution. Let's just do a couple of examples of this, but I want to show you these two illustrations first so that you can understand these two statements that are up here. Let's imagine that we have a beaker, and this first beaker has, let's say, 1 liter of water in it. And if I was to put glucose in this solution, one of the things to remember about this glucose is that it's covalently bonded. And that means that when glucose goes into solution, it stays together as a glucose molecule, or as several glucose molecules, and these do not separate. So if I put 1 mole of glucose into solution, I wind up with 1 osmole per liter, if this was in fact 1 liter, as we just said. Now let's take a look at sodium chloride, which is a different situation. Let's assume once again that we have in here 1 liter of water, as we did in the other beaker. And now I'm going to take sodium chloride and I'm going to put it into solution. Remember, sodium chloride is an ionically bonded compound. And if I take sodium chloride and drop it in the water, notice what happens. This actually breaks up now into sodium and chloride. So this breaks up into 2 particles, and that means that if I put 1 mole of sodium chloride into water, I wind up with 2 osmoles per liter. In other words, this is double the osmolarity that the solution of glucose was. And the reason for this is it really depends on how many particles are yielded after I put something in solution. And that's the reason for the formula that you see over here. So we say that the osmolarity, once again, is equal to the number of moles per liter times the number of particles yielded in solution. So let's do a couple of examples. if I was to, for example, put 1 mole of sodium in a solution, and I wanted to know if I was putting that in 1 liter, so 1 mole of sodium in 1 liter of water, times the number of particles yielded in solution, we know that sodium itself can only yield 1 particle. There's only 1 sodium there, so that would be multiplied by a number 1, and that would in fact give me 1 osmole per liter. Let's take, for example, something a little bit different. Let's take the sodium chloride example that we had before. If I took 1 mole of sodium chloride now, and I put that in 1 liter, think about the number of particles that are going to be yielded in solution when I drop this in solution, and you'll notice that now we have 2 particles or entities that are going to come from each mole of sodium chloride that I put in the solution, and so that now is going to be multiplied by 2, and that means that we're going to wind up getting 2 osmoles per liter. I hope you see that. It's kind of important. It's an important concept for you to get. Now let's go on to the next concept, which are equivalents and milli-equivalents. As you see here, an equivalent is the positive or, this is an important word, negative charge equal to the amount of charge in 1 mole of hydrogen ion. So once again, an equivalent is the positive or negative charge equal to the amount of charge in 1 mole of hydrogen. Going back to the definition of a mole, if you haven't had chemistry, don't get panicky about this, but in 1 mole of anything, there are 6.02 times 10 to the 23rd particles. Okay, so if I had 1 mole of hydrogen ion, there's 6.02 times 10 to the 23rd hydrogen ions in that 1 mole. And since each hydrogen ion has 1 charge, that means I would have 6.02 times 10 to the 23rd charges, right? So positive charges. Now, what we say is that anything that has exactly this number of charges is equivalent or is an equivalent of that. Now, one of the other points I want to make here is that the sign of the charge is irrelevant. In other words, if I had 1 mole of chloride, even though chloride is a negatively charged ion, I would still have 6.02 times 10 to the 23rd negative charges in that mole, but we're really only concerned with the number, not the sign. In other words, for purposes of calculating equivalence, plus and minus are really equal. Okay, and this is for the purposes of calculating the equivalence once again. So the sign of the charge is basically irrelevant when we're calculating these things out. And as we said, a milli-equivalent is equivalent to 1,000th of an equivalent, just like we did with the osmoles. Now, our formula for calculating these is that the number of equivalents, if we want to figure that out, is equal to the number of moles, or number of moles per liter, times the valence of a particular ion. Now, by valence, of course, we're talking about the charge. For example, if we have a sodium ion like this, we have a valence of 1. If we have a calcium ion like this, we have a valence of 2. So there are 2 positive charges there. If we have a phosphate ion, which we'll look at a little bit later, like this has a valence of 3. So let's look at a couple of examples. Let's assume that I had 1 mole of sodium here, and we know the valence of sodium is 1. We would just multiply that by 1, and that would be equivalent to 1 equivalent of sodium. Can you see that if we have 1 mole of sodium, that means we have 6.02 times 10 to the 23rd positive charges in that 1 mole, and that's exactly the same number of charges that we had in 1 mole of hydrogen ion. So we would say that these are equivalent. Therefore, we say that this is 1 equivalent of sodium. If we have 1 mole of calcium, and we know from above that calcium has a valence of 2, so 2 plus, we know that the valence is 2, therefore this would be 2 equivalents of calcium. So in 1 mole of calcium, we would still have 6.02 times 10 to the 23rd particles. However, since each particle has 2 pluses, or 2 charges, we would have double the amount of charge that we would in an equivalent mole of hydrogen. Therefore, this is 2 equivalents of calcium. So what if we wanted to match up the amount of charges in calcium with the amount in hydrogen ions? So we would say that in 1 mole of calcium, we have 2 equivalents. And what I want to know is how many moles of calcium would I need to have one equivalent? And I think you can see the math is relatively simple. If we multiply by one equivalent on each side, these cancel out. We multiply by one equivalent over here, the equivalents cancel out. We're left with 1 over 2, and that's going to mean that we need 0.5 mole of calcium to make one equivalent. I hope that makes sense to you. So now in half a mole of calcium, we have exactly 6.02 times 10 to the 23rd positive charges, just like we do in 1 mole of hydrogen ion. Okay, and that's the way we kind of work this stuff out. And it would be the same for any of the different valence of an ion that we work with. Okay, so hopefully this explains these a little bit. And what we're going to do now is we're going to terminate this lecture, and we're going to go to lecture 17, Part B, where we're going to go on and talk about some stuff that's not so mathematical. And we'll get back to talking about body fluids and electrolyte balance and water and acid-base balance. I'll see you there.